From our recent videos, we know that the response of a material to the external electric fields in terms of the polarization that is created, and let's stay now with the third order, is such that it can be written in terms of an integral over 3 times. Of course, if it were a different order of response, we would have a different number of times. And in general, in this type of response, it's always the number, the order of response corresponds to the number of time intervals that we have to integrate over. So polarization is a vector. In principle, the input for this expression is 3 times a vectorial electric field. So the output has to be a tensor. I will write it out this way. An arrow going in both directions. And we stick to the third order, and it's a function of the intervals tau 1, tau 2, tau 3. And we have actually already shown how that dependence looks like. Here we have the dependence on the electric field, where actually there's always t inside, and there are delays tau 3, tau 2, and tau 1. Okay, so here we have 3 vectors actually coupling into a single tensorial function, and it gives a vector out. We have actually been working with something somewhat simplified, because we have taken the polarization vectors of the fields out, combined them with the transition dipole moments that are now inside the S3 functions, and written for a two-level system. We have written a vectorial response function that looked somewhat more simplified. So it would be a vector depending on tau 3, tau 2, tau 1, and we had I to the third power, we had D to the fourth power. This was the transition dipole moment length. In fact, the correct way to write this would be D to the third power, and here we would have still one of the D's as a vector divided by h bar to the third power, and here we had a trace over some simplified operators. There was an operator M, which was basically just the projectors out of the transition dipole moment operator, evolution operator in tau 3, a superoperator M. Again, we'll repeat its definition soon. We had these type of dependencies, and then one more M, which acts on rho minus infinity, which is the initial state. And the M superoperator acting on an arbitrary operator A is a commutator with M acting on A, and the M was basically just the bare transitions between the ground and the excited state. So this is how we wrote initially the response function or response vector, but let's stick to the response function nomenclature. And we also found that there are 8 terms inside the S3. So S3 can be written, you can think of it as a combination of 8 different functions, so from 1 to 8, Rn of the third order, tau 3, tau 2, tau 1, and we have actually already written some of these R's out, or we have written out some sort of 8 terms and said roughly how they are going to look like. That rough estimate will not be enough. We actually have to go way deeper into the evaluation of the individual components of the response function. That's one thing. The other thing is, for a two-level system, it's still easy to keep the terms just organized in terms of equations, but it's clear that realistic systems have way more levels than just two, and we will have to organize the response function components in some way more advanced manner. And in fact, there is a methodology which we will introduce now, which allows us to do just that, to keep a good bookkeeping on the individual response functions or contributions to the response function, and actually somehow graphically see their individual components. And that nomenclature is called Feynman or double-sided Feynman diagrams. So double-sided Feynman diagrams. So the double-sided Feynman diagrams are just some sort of a simple graphical representation of the action of the commutators on the initial operator or initial electronic density matrix, reduced density matrix to the or density matrix reduced to the electronic degrees of freedom. So that operator initially looks like this, and there are various actions of various operators, actually transition dipole moment operator most from the left on and the right of this construct out of the state vector or vector representing the initial state. So we have changes of electronic state due to interaction with the electric field of the light from outside. And then we also have time evolution of the state along those intervals tau 1, tau 2, and tau 3. And this is denoted, this whole thing is denoted by something that has a vague appearance of a Feynman diagram that you might know from some other parts of physics. So let's write first an arrow of time going from bottom up, and actually two of them. Why? Because we will keep time evolution of both bra and cat of the transition of the density matrix. And the initial state in this diagram is the one in which we are in the ground state in both bra and cat. What we want to account for here is the action of the superoperator M. That superoperator M acts also from always from both sides, and that's why we always have from each action two contributions to the response function. And we will follow just one. So we will, let's say, have first an action of a transition dipole moment operator from the left. That will lead to a new state. It will excite the left side of the density matrix operator from G to E, and on the right hand side we will still have G. And after that the system will evolve in time for the interval tau 1. The evolution of the ground and excited state in here is different, and in the standard description that the time evolution is action of a superoperator, evolution superoperator on this initial state, but we are not here in the initial state, but in a state that is shifted up by the action of M. This actually, we also know that if we had no environment, or if the system were closed, we would be able to describe it by an evolution from the left and an evolution from the right. And these things would be different because we keep evolving on different potential energy surfaces, or let's say we keep evolving at different electronic states on the left and right hand side of this operator. Okay, so we evolve for time tau 1, and after time tau 1 there will be another action of the commutator, and that can come from the left and from right, or from the right. So let's assume it comes from the right. So we have the superoperator M acting again, and we choose the one of the actions which comes from the right. And we should not forget there is a minus associated with that. So now we will have again a change of state, and from G we will go to E, and on the left hand side we will also be in E. And this state of the density matrix, or perturbed density matrix, is going to evolve for time t2, tau 2. And this evolution in principle means nothing, because we don't assume that there is a possibility to de-excite the system. So we evolve in the excited state until we are hit again by the action of the commutator. And let's say, because we have both options obviously, let's say that this action comes from the left. And what it has to do now, it brings again a new set of states. So from E we'll get to G, and we keep to E here. And again we evolve for some time tau 3. And now the last thing that we have in the construction of the response function is a multiplication by the operator mu of the transition dipole operator, and construction of a trace. That multiplication we always write on the left hand side, but we also know that under the trace we can rotate all operators. So in principle we could write mu to the right hand side too. And the last step is if we multiply from the left, we kind of emit the E, because what happens here is that due to this response we actually shine light. So the last step is some sort of a stimulated emission, multiplication by mu from left or right, and we end up in a state G. Trace over that is non-zero, so our diagram, our contribution, is going to lead to a non-zero contribution to the response function. Now, this might look like we've been just playing with colors and drawing things, but what we've done is much more non-trivial. We have, for instance, found that a contribution like this will have a minus sign. We will also see that there is a possibility to see in advance what kind of phase factors the contribution like this will have. And we also know that there are in principle 8 contributions that look like this. And if we know, the only thing that we need to do now in order to write out all the 8 contributions is to actually combine the actions from left and right in all possible ways. Now we noticed that this particular diagram has a minus sign. So out of those 8 diagrams, we will see that there are 4 with plus sign and 4 with minus sign. So let us now write out or construct all the diagrams with a positive sign. So we write out all the possible diagrams with positive signs. So they will always have this box structure with 3 intervals in them. So we can write 4 different boxes. They always start with GG. I will be less colorful now. And there will be 1, 2, 3 interactions, and the diagram will be closed by some sort of an emission. So let's write 4 diagrams like this. Okay, and let's now put the arrows in all possible ways in so that the sign, overall sign of the diagram is plus. That means that there has to be either 0 actions from the right hand side, or there must be 2 actions from the right hand side. Well, we will see why that is. Let's start from the left hand side. So we'll go to E, G here. Then we can go from the right hand side, E, E. And what we can do now is go back. I will start to write the arrow in such a way as if we were adding energy to the system. Here we had the transition from G to E, for instance, and here we have from E to G. That is an emission. So we have here E and an emission out of here, and we are at the GG. This is fine. This has a minus, and altogether this gives a plus sign. So that's one of the possible ways to write the diagram. Now let's have a look at another option in which we start from the left and now add no actions from the right. So here we would have to leave the E in favor of G, and here we can add E again, and we are in GG. So there's nothing in here. This is clearly a plus sign. Well, all other options which would start from the left hand side would already have to have a minus sign in order to we need to use all combinations, but they have to be different. So let's start here with a minus, E, G. Here we go from the left to E, E. We leave again to G, and here we go to GG. And we have actually one more option that starts from the left to the E and immediately goes back to G and stays in G, whereas on the other side it's G. Here it's G, but here we add 1 to E and leave again to G, G. So the last wavy line is a contribution of that mu or m, the last operator, the lowercase m that closes the response function. And as you can see, even the contribution here has 2 minuses and therefore is a plus, and here we also have 2 minuses and therefore is a plus. So those are the contributions with the plus sign, and interestingly, if we wanted to construct those with the minus sign, we would actually find that they will always be mirror image of one of the existing diagrams already. So if you put the mirror in the middle of everything, you can actually find that this is one of the ways how you get a minus sign diagram. For instance, in this case, we would start from the left and then we'll go to the right, which we also have above here. But the last interaction would not be from the right, but would be from the left. I mean, the last of the 3 interactions before we add that arbitrary wavy line. That one can go actually from left or right without a difference. Okay, so that means we have 4 different contributions, and then we have in addition 4 contributions that have a minus sign and are actually Hermite conjugated to them, to the original diagrams. Because if you flip all the brass and cats, that's basically a Hermite conjugation of the operator, and at the top of it, at the end of it, you make a trace which ends up to give you actually a complex conjugated contribution. So I will now do some sort of or introduce some standard notation. The first diagram corresponds to a response which is called R1. The one below it is a response function called R2, and that's not that I'm just naming them with numbers, but the shapes of these diagrams actually really correspond in a standard way to these numbers or to these RNs. And everybody who works in the field actually knows what's the shape of R1, R2, R3, and R4 are. We will also learn their properties and what's so important on them. So we have these response functions that will be the contributions to the total response function. And we, for instance, can see that out of the R1, we can make the minus R1 star response function, which will look like this. This is going to be E. Here we start with G, G, E, E. This is G. Out here, G, E, and we can go to GG. This is precisely a flipped version of the R1. And interestingly, there are no other possible contributions than these 4 and their complex conjugated. So the 8 terms that we were looking for, they can all be written in terms of those 4 different pathways with positive signs. So we can write that S3 as a vector as a function of tau 3, tau 2, tau 1 corresponds to a sum over n from 1 to 4 Rn tau 3, tau 2, tau 1 minus Rn star tau 3, tau 2, tau 1. So this is one of the discoveries we have made about the structure of the response function. In fact, it is a sum of 4 contributions minus their complex conjugated contributions. Now, each diagram corresponds to a single contribution to the response function, and we will use the diagrams very often, or we will be able at the end of this lecture somehow think in terms of the of different diagrams that are possible for each molecular system, and we will always be able to assign to the specific diagram a specific response function. Those response functions, individual contributions to the S3, are called Liouville pathways. Liouville pathways are basically some individual substructures of the response functions. We denote them, or we graphically show them in terms of the diagrams. So graphic representation of Liouville pathways is either in terms of the Feynman diagrams. So I'll write one Feynman diagram here. Again, actually carries a lot of information that will be useful later. So for instance, this diagram, I'm repeating it not for the first time here. So this is the one possible Feynman diagram. But sometimes we can actually highlight just the structure in the so-called Liouville space. They are called Liouville pathways because they are pathways in the Liouville space. Pathways Well, if we haven't been very careful in saying what is a Liouville space, then I have to say it now. So Liouville space is the space of operators, just as the Hilbert space is a space of vectors. We have Hilbert space, we have a basis of the vectors G and E. That's the basis. In the Liouville space, we also have a basis, and it contains these operators here. So we can have this E, G, and E, E, E. Of course, for a larger Hilbert space, there is also a larger Liouville space. So the diagram that we have written here actually goes through a certain pathways in the Hilbert space. One pathway in the Hilbert space. So we start with this. The first action, which comes from the right, changes the right hand side vector into GE. And then we have an action from the left, which we can, for instance, denote by dropping down with this diagram, and that lifts us to EE. And then there is yet another action from the right, and that gives us EG, and then we go down to G, whereas the last action is actually the action of the operator M and not the superoperator. So here we have M, and M, and this here is the M operator. So a diagram like this also denotes somewhat completely the individual Liouville pathways. Now, it is clear that if we have many levels, it might become difficult to write out all the pathways, but we will also see once we start describing individual nonlinear techniques that individual diagrams correspond to contributions, like for instance stimulated emission or excited state absorption or ground state bleach, and we will be able to explain all these properties just on the diagrams, and eventually also on the pathways, but the diagrams are way more useful in fact. Okay, now we have to start picking different characteristics of the individual pathways to find out what are their most important characteristics. One of them are the phase factors that these pathways have in the times tau 1 and tau 3. So I'll just make a little note. The most important characteristics of the Liouville pathway, of each Liouville pathway, is the phase factor in tau 1 and tau 3 intervals. So again, we'll draw one diagram, the diagram R2. So we start with acting from the right hand side, get us to GE. Then we have an action from left hand side. This will get us to EE. And then this is followed by dropping back to G on the right hand side. So it's EG and what could be called an emission, which will get us to GE. So now you can see that in the time intervals, which I will denote here, tau 1, tau 2, tau 3, in tau 1 we are actually propagating a coherence between the ground and excited state. That is something that will evolve in this particular case, because you can see that there is this side which will evolve as e to the power of minus I epsilon g divided by h bar tau 1, and on the other hand we will have e to the power of I epsilon e divided by h bar tau 1. The plus is here because this is a bra vector. So altogether, this gives us a phase factor which looks like e to the power of I omega eg tau 1, where obviously omega eg is equal to epsilon e minus epsilon g divided by h bar, as is usual. In a very similar manner, we will see that the third interval in tau 3 evolves as e to the power of minus I omega eg tau 3. The interval in the middle, there's basically nothing evolving there, roughly speaking. So there's no phase evolution, or at least not in this diagram. So having a diagram like this written, we can actually, and that's the most important thing on it, we can actually reconstruct the corresponding response function. Response function is really a function of tau 1, tau 2, tau 3. So this is a diagram corresponding to R2 as a function of tau 3, tau 2, tau 1. This thing has a prefactor I divided by h bar to the third power. Roughly speaking, I mean, we will handle all these things later. There is d to the fourth power. And then there is something happening behind this, which is enclosed in a trace. So in order to construct that thing which is in the trace, we have to follow the diagram from bottom up. So we start with the initial state. I'll write it down here. It's GG, and we start with action of the M from the right. Now when the M acts, it actually leaves the E from outside. So I can put here E, and nothing changes. I put it here just in order to see that there is E outside of this. So this is going to evolve in time interval U tau 1. And because this is GE, this is sticking out the GE outside, it's an evolution of the coherences, so this will evolve using the evolution superoperator element GE. Again, you read something like this from the back, so this starts with GE and ends up with GE due to the secular approximation. Now we close this because this is how we get in the interval in the diagram before the second interaction. The second interaction is done from the left hand side. So we have M here, and the G will be lifted to E. So I can also add here EE, and nothing changes. And that's written here just to make sure that we see that we are now in the state EE, or we are in a let's say in the Liouville space, we are in EE. There will be an evolution by an element EE. We have a two-level system, so there's no other state to which we can go in the excited state. So we propagate and stay in that state. This is basically 1 in this case. In a general case of more than one or more than one excited state, this will not be true, but certainly it's true here. So with this we got to the end of the second interval, and we have an action of M now from the right hand side. So we act with M again in green, for instance. So M here, and obviously from E we can only get to G, so I'll put GG here just to show how we evolved in time. This whole thing is now sticking out EE, so it's going to EG, so it's going to evolve as EG tau 3. Now we are at the end of the third interval, and we close it with an action of m from the left hand side, and this whole thing will be traced over. So there is a trace acting on this. And because trace is basically just taking, so what we have on the right hand side, G is sticking out, and here we have M acting on E, so also there is a G sticking out. Because M carries just one, there's only as we've shown already, there's nothing there except for a projection from E to G. All the elements that are inside the trace evaluate into one except of the evolution superoperator elements. So if we now collect all the terms together, this equals I divided by h bar to the third power, d to the fourth power, and then we have u e g tau 3, u e tau 2, and u ge tau 1. Nothing else in here. Now, just to get that crucial insight into how this function actually looks like, is we realize that the main thing that happens to the coherences EG is that they evolve with the phase factor, which we have already denoted here next to the diagram. So we will assume, let's copy some factors here. We will assume that we can write UEG using some slowly evolving part, which will mainly describe the decay of the coherence, and an additional term, which will be nothing else than just the exponential e to the power of minus I omega EG tau 3. And well, the second interval is already slowly evolving, so we can put a tilde on that, and then there is GE slowly evolving, and an additional factor I omega GE tau 1. So this is something we have to put in here, and we can write the R2 tau 3 tau 2 tau 1 as something with this prefactor, then the slowly evolving part where we collect all these green elements here into something like R tilde 2 tau 3 tau 2 tau 1 and e to the power of minus I omega G tau 3 minus tau 1. So the omega EG is a frequency, is roughly frequency of light, because we are exciting resonantly in the nonlinear spectroscopic techniques. And the change which undergoes the R2 in the times tau 3, tau 2, and tau 1 is much slower than the oscillation due to the optical frequency. So we could actually, I mean, a lot will depend on how the R tilde looks like, but many things, those that we will investigate now in this lecture, will actually depend on the shape of this factor here. Well, interestingly, we can write down for all four pathways, Liouville pathways that we have chosen with the positive signs here, the pathways R1, R2, and R3, we can write out the phase factors just from looking at their diagrams. So let's go to the diagrams and see the R2 that's here has GE down here. So as we said before, this leads to the E I omega EG tau 1, and here minus I omega EG tau 3, and you can see that R3 starts and ends with the same phase factors, whereas R1 starts with e to the power of minus I omega eg tau 1 and ends also with the minus I omega eg tau 3, and R4 does the same. So basically we can go back and write R1 tau 3 tau 2 tau 1 is equal, I mean all these things will be the same, R1 tilde tau 3 tau 2 tau 1 and e to the power of minus I omega eg tau 3 plus tau 1. So it has a different phase factor than R2. R3 has again the same phase factor as R2, so we have minus I omega eg tau 3 minus tau 1, and R4 happens to have the same phase factor as, so this is 1 here, this is 2, as R1. So this is R4. These tilted response functions, they can and in general have somewhat slightly different shape, or they look slightly different from each other, but we will, in our approximation, they will actually be very similar to each other. Okay, so we have two different types of phase factors. We have the one with minus and we have the one with plus. This difference will be really crucial. So we have two different types of phase factors. So why I'm not saying we have two different phase factors, why I'm saying we have two different types of phase factors? Well, clearly omega Eg is something that depends on the energy gap between the excited and ground state, and of course as we will have more levels, we will have phase factors which will be rephasing or non-rephasing with different frequencies. So we have to, we are interested here in the type of dependence on tau 3 and tau 1. So the first dependence that is very useful and important for us is this one, e.g. tau 3 minus tau 1. We call this rephasing phase factor. Rephasing refers here to the fact that when tau 1 is equal tau 3, this exponential gives 1. So e to the power of minus e.g. tau 3 minus tau 1 is 1 around this value of tau 1 and tau 3. Of course, another situation where this argument is 1 is when the difference and the frequency together give you a multiple of 2 pi. But again, as omega Eg is roughly arbitrary or can vary between different levels, if you sum up together contributions from slightly different energies, these things will never ever everybody meet in one value. So they will destructively interfere. The only situation in which, regardless of frequency, this phase factor can rephase is when tau 1 is equal tau 3, and as tau 1 and tau 3 are some sort of delays between laser pulses, as we will show later, this is something we can manipulate with. The other important phase factor that we have to investigate here is the one with plus sign between the times, and this is called non-rephasing phase factor. Obviously this thing is really, even when tau 1 and tau 3 are equal, this does not rephase phase factors with different frequencies. So it's actually a purely non-rephasing phase factor. And we will see that this effect, I mean the fact that one of the phase factor can possibly rephase at a specific delays tau 1 and tau 3, this will lead to the effect of photon echo, which we will also discuss within this lecture. Okay, so we can somehow go back to polarization and start to think what this specific result that we obtained, what is it going to give us? How can we use it? So we now know that P is this prefactor. Again, about the D, we will talk later. So the fact that this is actually a D to the third power, we may even write it just to remind ourselves. So the three Ds are actually already projected with the electric field, but the last D, transition dipole moment of the molecule, that's what's giving the polarization. So we have this integral, or three integrals, and here we have sum over n from 1 to 4 r n tau 3 tau 2 tau 1 minus something very similar, and three occurrences of the fields. Right. And because of the finds that we did earlier in this video, we can actually write it using those tilted R's, and we will look at a single contribution to see what the effect of the phase factors will be on the integral. Actually, we will show that there will be a dominant contribution which will come from a combination of the tilted R's and the electric fields. There will be some dominant contributions with matching phase factors from the electric field and from the response, and those things will classify, or there will be dominant contributions from different pathways with different actions of the electric field from the outside. In order to get to the bottom of that, we will now have to investigate a term, single contribution, which will look like this. We start with R2, tilted R2, tau 3, tau 2, tau 1, which is a phase factor of minus I omega Eg tau 3 minus tau 1, and it is multiplied by the electric fields with different phase factors, with different arguments here, and of course different phase factors is also contains phase factors that look like e to the power of I omega tau 3 and etc. And we will assume, very important assumption here, that the frequency of light will be roughly resonant with the frequency of the transition between the ground and excited state. Well, before we get to the bottom of this contribution, we have to start thinking in detail how the electric field from the laser that attacks the molecules in a spectroscopic experiment, how does it actually look like? So let's now continue discussion of the third order response, third order nonlinear experiments. And let's have a look at what is the most general way we can organize the pulses that would go into this experiment. Actually, third order does not necessarily mean three external pulses, but it can mean. So we will, in our discussion, assume that we have three pulses going from different directions and hitting the sample at certain time. So we will define the time so that the time 0, and we will see this from our theory also, that the time 0 will be defined in the middle of the third pulse. I mean, if we want to have a third order response with 3 pulses, we want that response to actually being generated only after the third pulse. So this is, let's say, how the envelope of the pulse will look like in time. That's the envelope AT, which is centered around 0, not in my picture, sorry. And this is an electric field given a certain frequency. It's a field of light given a certain frequency and going in the direction of the wave vector k3. Then we will have a second pulse which actually precedes it, a pulse that will be of the same shape, sorry again for my graphic misrepresentation, but going from different direction, and the electric field envelope is centered at time t minus some capital T. So it's going to be the same function a, but now shifted back in time by capital T. So we have a delay here between 0 and the time in the past that is of the length t. So this is basically the minus t position on the time axis. And we need yet another pulse, the pulse that actually hits the first of all 3 pulses, and that's going to be somewhere here, for instance, and it has a k vector k1 because it comes as a first, and this one is again back in time, separated from the second pulse by a time delay tau. So this location in time is minus capital T minus tau. And obviously if we assume that it has the same or roughly the same envelope, that envelope is T plus capital T plus tau. Okay, so this is sort of the time scheme of our pulses. They are also possibly coming from 3 different directions to the sample. So we can draw something like this: K1, K2, K3, and this one is the first, second, and third pulses, and they hit the sample and a signal is produced in certain direction. We will be looking at sort of already a certain chosen direction, which will be, the most interesting one will be the minus k1 plus k2 plus k3, but the justification of that we will provide later. Actually, we have been already discussing a combination of k vectors like this in one of the initial lectures. Now, what this picture, the time-dependent picture, actually looks like, or what does it mean for the electric fields that enter our equations for the polarization. So far we have E, that's already a scalar electric field, and actually looking at our arrangement, we can write down how this electric field looks like as a function of time and as a function of space. Well, the thing is, and the very important thing that we will have to sort of see clearly, is that the electric field depends also on space, and that this spatial dependence comes really only from the spatial factors of the plane waves. So we have A1 at t plus tau. That's the envelope of the first pulse. Then we have its frequency, and because the pulses are usually created by splitting off from a single pulse and by generating delays, we have to have the delays in the phase relations of these exponentials also. So we have t plus capital T plus tau here, and plus I k1 r, that's the first contribution to the pulse. The second contribution is A2. Now we write A1, A2, A3 because they don't necessarily have to be exactly the same, but we will mostly assume them to be the same. Why not to denote them with different numbers here? So the second contribution will look like this, and we have plus IK2 R, and the third contribution is the last pulse K3R, and of course there are complex conjugated terms because the field is real. So we have altogether 6 terms. And what does that mean for us? Well, that means that we have really a lot of terms in this multiplication of 3 fields that we have inside the integral that integrates into the polarization. So this is 6 to the third. That is 216 terms. That's a lot. That's a lot. But on the other hand, we, for instance, already know that the signal will have all the possible combinations of the k-vectors and the corresponding combinations of the frequencies. And we can choose, we can in principle choose randomly, but we can choose one of them, and we know that it will propagate in a specific direction. We have actually seen the phase matching condition, which tells us that if the polarization term has certain specific k-vector dependence, or actually r dependence, when we integrate along that direction, the signal gets generated only in that specific direction of a combination of the k-vectors. So we can actually well separate individual contributions for different combinations of k-vectors, and we can have another specific condition on our signal. We want that signal to appear at the frequency which is same or similar as the fields that we sent in. So if we sent in an optical field of the frequency omega, we want the same frequency back. What does that mean? If we have 3 multiplications of e's, we also have e to the power of I, and now all different combinations of k-vectors, and the same contributions, same combinations of the frequency. So obviously, if we want this to be roughly looking like this, then 2 of the frequencies have to cancel somehow, and with them we also have an associated signs of the k. So we have to choose, in order to get a frequency omega, we have to choose such a combination in which at least one of the k vectors is taken with the minus. And we can do that. For instance, our signal now will be, let's take the minus at the first one. So this is the k vector into which we are going to look at first. Well, there is of course an interesting question associated with that, like how is this choice going to influence the integral that we have in evaluation of the polarization? You know, we have shown, for instance, that the different contributions to the response function, that they have different phase factors, and with these phase factors we have to integrate the contributions from the 3 electric field. There is a chance that some of the phase factors will actually leave in that integration some highly oscillating terms, due to which at the end the integral will be nearly 0. And there is a chance that we will find such phase factors that will actually cancel out completely, and then we will have an integral of a slowly evolving argument, which can easily be something non-zero. So this is roughly the idea we will follow in the evaluations that will follow. So now let's have a look at the electric fields, and we have to assume also not just that we will look at the signal in this direction, minus k1 plus k2 plus k3, but we also want to clearly separate the pulses, that they come in specific order. So order of the pulses, or order of the pulses will be actually well respected. So the third pulse, the last one which interacts, must be this one. This is the last pulse. That will be the pulse with the phase factor ik3r. So it also has to be the third pulse. This will be the third pulse out of our order. That's the pulse which will have the k3 contribution. So we will assume that et minus tau 3 is a contribution from this field. I mean, what we are doing with is we can actually go through all the possible contributions of the product of e's. We will look at them and we will find out that they have different phase factors. So let's have a look now at the one in which the third pulse, or the one that comes the last, contributes with the phase e to the power of ik3r. So that means this is the contribution that looks like this, plus ik3r. The pulse that precedes it, the one that has the following argument, will be the pulse which comes with the ik2r phase factor. So it must be the contribution a2 t plus capital T minus tau 3 minus tau 2 e to the power of I omega t plus t minus tau 3 minus tau 2 and I to the power of k 2r ik2r. Okay, that's it. And the pulse that comes the first, the one that, due to these three arguments or three appearances of the taus inside, is the one that comes the absolutely first. That one must come with I to the power of minus ik1r, and that contribution will read a1 star. It can possibly be complex, plus tau minus tau 3 minus tau 2 minus tau 1, and the same is going to be the plus I omega t plus capital T plus tau minus tau 3 minus tau 2 minus tau 1 and e to the power of minus I k1r. So we have these three contributions, and we can write down how is this response function, or the part of the response function which will have inside the R2 pathway, and this specific choice of the contribution of the electric fields, how is it going to look like? I repeat again that we have all 8 pathways inside the integral, and we have all 216 different combinations of the terms under the integral. We are now trying one which takes the R2 pathway and which takes this specific contribution order in which the et minus tau 3 contributes with the k3 part of the field, and the other two contribute with k2 and minus k1. We will see that this particular choice leads to something nice, and we will then also discuss how possibly the other choices do not lead to anything nice. All right, so let's start now with one of the 8 times 216 contributions to P, and that one will look like the three integrals, tau 3, tau 2, tau 1, and here we have the R2 tilde. I repeat that the dependence of R2 tilde on tau 3, tau 2, and tau 1 are relatively slow, much slower than the dependence on this optical frequency contribution. So that's what we have from the R2, and it continues with all the three contributions of the envelopes. That's again something that changes relatively slow. And here a 1 star t plus tau minus tau 3 minus tau 2 minus tau 1. And now the most important thing here, the phase factors. So e to the power of minus I omega t minus tau 3, that's the first one, minus I omega t plus t minus tau 3 minus tau 2, and plus I omega t plus tau minus tau 3 minus tau 2 minus tau 1. Okay, and the last very important factor, because that's the spatial factor, minus k1 plus k2 plus k3 r. So let's start from the back. So this phase factor, when it comes to space, is the only spatial dependence of the response. The molecules that actually give the response R2, they are essentially identical, and it doesn't matter where in the sample they are, but they always react just to the electric field, and that electric field is the same everywhere in the sample except that it has a different phase specified by this phase factor, and that's why the P, the total contribution, will have all these combinations of the k vectors in it. And as we know, the contribution that has a specific combination of k vectors will travel and will accumulate along that direction in the sample, and the electric field will at the end leave the sample as a signal. Okay, so that's the spatial dependence. And now we have some important things that we will sort of stop considering for a while, and that's the slow part. The envelopes and the R2 tilde are the slow parts, and we will be now interested only in the fast oscillating phase factors. Those fast oscillating phase factors, however, here contain quite a lot of things that could be cancelled. For instance, this t and this t can be cancelled, this capital T and this capital T can be cancelled. Also this tau 3 and this tau 3 can be cancelled, and this tau 2 and this tau 2 can be cancelled. So altogether we can identify terms that still depend on some parameters such as the external time and the delay between the first two pulses. And then there are integration variables, tau 3 here, tau 3 here, tau 3 here, tau 1 here, and nothing else. Everything else is slowly oscillating. So the contribution that we have here can be written as e to the power of minus I omega t minus tau, the three integrals, and then we have R2 tau 3 tau 2 tau 1. We have A3t minus tau 3, A2t minus, no, t plus, capital T minus tau 3 minus tau 2, and A1 with a star, t plus tau minus tau 3 minus tau 2 minus tau 1. And this is multiplied by the factor, phase factor, that comes from the R2, that is with e to the power of minus I omega eg tau 3 minus tau 1, and the factor that comes from the only surviving factor, which depends on on tau 1, tau 2, tau 3. Actually, tau 2 has disappeared. This is the factor that looks like this. Now, omega eg and omega are positive numbers. One of them is the transition frequency of the two-level system, and this is the frequency of light. And those things should be resonant. I mean, this is one of the conditions of actually doing this experiment. So we can say that, first of all, omega eg will roughly be omega, and almost always, because even though we would not have exact resonance, especially when we have many levels, you know, exact resonance is impossible. But let's now assume for a short time an exact resonance, because we have a two-level system. So two-level system plus exact resonance means 2eg equals omega eg equals omega, and then we can write that the polarization pt is basically roughly e to the power of minus I omega eg t minus tau, and this integral over only the slowly evolving part. We can actually make yet another approximation, and that will be the approximation of ultra-short pulses. I mean, here we are breaking a little bit the condition that the envelopes have to evolve slowly. In literature, sometimes people discuss this situation as working with a physical delta function. We will assume that the AT is actually some, you know, A0, some envelope, and delta function, which means, or this is supposed to represent a very short pulse. However, it should be physical pulse. I mean, the actual delta function has in frequency domain, its spectrum covers the entire spectral axis, so there's no end of it, whereas the sort of physically achievable ultra short pulses, they still actually come in certain spectral region, so that you can assume that you excite resonantly. There are simply some levels that you don't excite. For instance, you don't excite directly the 2-exciton band or the sort of second excitation levels. We have discussed that we will need a ground state and then 2 bands of levels separated roughly by the frequency domain, and our ultra short pulses do not reach over to this second band. So that's a physical delta function. We will assume that that A does really concentrate only in a region around 0, very narrow region around 0. Yet the resonance conditions that we've been using in evaluating the response function, and we are using now, or we will discuss now, they are still valid. So if we assume that this is really true, so there are very short, ultra short pulses, then the A3 t minus tau 3 actually means the presence of this in the integral, means that tau 3 is equal to t. And we continue, t plus t minus tau 3 minus tau 2 then means that a2 is t minus tau 2, which in turn means that tau 2 is equal capital T. And obviously the a1 is also going to do the same, to limit the values of the integration variables to just one value. T1 is equal tau here, and we don't have to integrate anything. So if you remember how the polarization looked completely, and we have pt I divided by h bar to the third power, we have d to the fourth power, then we have whatever was in front of the integral, and we have r2. Now we don't have to integrate over it because we have used the delta functions, and we have r at t, at capital T, at tau, and this is all multiplied by, you know, a0 to the third power, and we obviously have e to the power of I minus k1 plus k2 plus k3 r, and this was just one term that we have evaluated, plus other terms. And there are plenty of them. You know, we said it's 8 times 216 of different terms. So we now have to somehow consider what else is possibly appearing under the integral. I mean, it was clear that the r2 was not cancelled in this integration only because of its phase factor. So there's a you know, truly tremendous importance of the phase factor of Rn makes it survive. For this is the it's crucial for survival of the term under the integration. So because R2 has the same phase factor as R3, also R3 will contribute. So there's no doubt that R3 has exactly the same function as R2. So R3 T tau will also contribute. Now, what about the other terms? So what about R1 and R4? Well, we still have those three integrals. We have R1 and R4 with the phase factor minus I omega Eg tau 3 plus tau 1, and from the field we have e to the power of minus I omega tau 3 minus tau 1, and obviously this does not lead to cancellation. So here we get e to the power of minus I omega Eg plus omega Eg plus omega multiplied by tau 3. So this is a fast oscillation. Integral goes to 0. Integral is roughly 0, at least in comparison to other phase factors. So that means that we can also investigate all the other terms. So out of the positive pathways, the ones with positive signs, so R1, R2, R3, and R4, we found only R2 and R3 to contribute. We can ask also about R1 star and the others. So R1 star has a phase factor e to the power of I omega e.g. tau 3 plus tau 1. This will lead to fast oscillation in tau 1. R4 star has exactly the same factor, and R2 star has e to the power of I omega e.g. tau 3 minus tau 1, which will lead to fast oscillations in, well, in fact, both in tau 1 and tau 3, and R3 star is exactly the same. So out of all the 8 possible contributions, only R2 plus R3 pathways contribute to the signal in the direction minus K1 plus K2 plus K3, actually under yet another condition, and namely that we still have we have the same order, or let's say order of pulses is 1, 2, 3. We have to take this, we will discuss of course this in detail, but now let's not forget that we don't only look into the direction minus K1 plus K2 plus K3, but we also have an order of pulses 1, 2, 3. This is very important. We have not really discussed it yet, but it was a clear condition that we set at the beginning. So let us now investigate a situation in which we keep the same order of pulses, but we look at different direction. And we choose the direction minus K2 plus K1 plus K3, which is the same as K1 minus K2 plus K3. So we are now looking, we have the same order of pulses. So K1 comes first, the K2 comes second, but we are looking into the direction where the pulses K1 and K2 are switched. This again means that the first pulse that comes, t minus tau 3, will be the e to the power of K3 pulse, K3R. So there's going to be a 3t minus tau 3, nothing changes here, minus I omega t minus tau 3 plus I K3R, then e to the power of t minus tau 3 minus tau 2, e to the power of, and this is the second pulse, and that has to come with minus K2R, a star t plus t minus tau 3 minus tau 2, e to the power of I omega t plus t minus tau 3 minus tau 2 minus IK2R. So, I mean, now we have actually two things at hand which allow us to pick this particular contribution. Why we write it? Well, we have very short pulses. So this is the only contributions that can actually occur. I mean, the second pulse still comes the second, and we are looking at a specific direction, and we know that only the response with that specific combination of k vectors contribute there. So we know that into our direction we will only have these contributions that we are writing now. And the third pulse, no, the first pulse in fact, in the order of appearance in the experiment is going to be the K1, which is now, unlike before, this is now not complex conjugated. The complex conjugation depends on the choice of the direction k. K plus IKR. Right? Now we have to look again, because you know there was this complex conjugation in it, so there will be a different phase factor attributed to the field. So if we take the three fields, the phase factors are e to the power of minus I omega t minus tau 3, then there is plus I omega t plus capital T minus tau 3 minus tau 2, and minus I omega t plus capital T plus tau minus tau 3 minus tau 2 minus tau 1, and this equals, well, there will surely be again some cancellations. For instance, this and this and this and this and this and this and this. So all together I'm going to have I to the power of minus I omega t, but now plus tau, and e to the power of I omega tau 3 plus tau 1. And this, if you remember, is the so-called non-rephasing phase factor. Or actually, it's just its opposite. And because it is its opposite, the only part of the nonlinear response function that will survive the integration will be the one with the true non-rephasing pathway, a non-rephasing phase factor. So we can conclude that in the direction of k1 minus k2 plus k3, when the order of pulses is 1, 2, 3, meaning k1, k2, k3, we get non-rephasing pathways, meaning contributing to the nonlinear response. Okay, so that is, it seems, just by looking at different directions behind our sample, if we send the pulses from 3 different directions, we are going to have different types of responses, which is very interesting and will lead to all sorts of possibilities when it comes to experiment. Now we have to look at another possibility that we have. Well, it's not only that we can change the place where we look, but we can also not change the place where we look, but for instance change the ordering. So let's have a look at the different, let's say, different ordering now, and the same direction, meaning the original one. We will be now looking into the direction ks equals minus k1 plus k2 plus k3, but the order of pulses will be 2, 1, 3. What does that mean? That means that e to the power of t minus tau 3 will be again the pulse with e to the power of k3r, that is a3 t minus tau 3 e to the power of minus I omega t minus tau 3 plus ik2r. Second pulse will be now the one with k1, and it will be complex conjugated. So t plus t minus tau 3 minus tau 2. Well, this will going to be a1 star t plus t minus tau 3 minus tau 2 e to the power of I omega t plus capital T minus tau 3 minus tau 2 minus ik1 r, and the last pulse, or no, first pulse to appear at the sample is going to be the pulse number 3, a t plus tau minus tau 3 minus tau 2 minus tau 1. I think this is in fact wrong. We should have 3 here, and this is the pulse with k1. That's the first one appearing at the sample. And e to the power of ik1 r. Okay. And actually, well, it's not so difficult, because it's exactly the same as before, where we changed the direction, that the phase factor that we get is the minus I omega t plus tau, and therefore also e to the power of minus I omega eg t plus tau, which is the non-rephasing phase factor. What does that mean? Well, that means that by switching the order of the pulses and keeping the same direction of the experiment, we get the non-rephasing pathways too. So to switch the pulses, so to switch the place where we look from minus k1 plus k2 plus k3 to k1 minus k2 plus k3 is the same as changing the order of pulses in the direction minus k1 plus k2 plus k3. I mean, it makes all the sense, basically. We are changing the sign of the second pulse, in fact, or the order of appearance of the second pulse between the first and second pulses. So, okay, this gives us sort of lots of material for thinking. In the next lectures, we'll try to organize all the possible experiments or all the possible signals that we can see at different places and with different pulse orderings in our experiment. We should also not forget that we have finite pulses, and if the finite pulses overlap, there will be contributions that mix a bit this nice order that we have now introduced in everything. But, you know, in this lecture, we need to keep things simple, so we will still continue assuming that our pulses do not overlap. At some point, we will make some review of what the overlap effects are.